Okay, so what were the core concepts from our PCR module? So first are about VNTRs and what they are, why they're different from person to person. So variable number tandem repeat regions, so these are regions in our genome that have repeats, one right after another, and the number of repeats that a person has varies from person to person. So these are regions that are useful in identifying somebody based off of their DNA. So we picked one of these regions to amplify in a PCR reaction to show you all what alleles you have and to demonstrate the techniques of PCR. So PCR, polymerase chain reaction. So it has 3 steps in PCR. So you first denature your template, right? So you have double-stranded template DNA that you put into a PCR reaction. You denature by heating to 95 degrees, so pretty hot, and your strands now separate from each other, exposing their bases so they can base pair with something else. After you denature, you cool it down to maybe around 55 degrees, and this allows your primers to anneal. Primers are short DNA sequences, right? So, okay, during this annealing step, your primers are free to find their complementary sequence on your template and bind to it. Okay, so the temperature of annealing versus the melting temperature of your primers is really important. If your annealing temperature is too high, well, you're going to denature your primer off your template. If your annealing temperature is too low, your primer can bind non-specifically. Okay, so you want the right balance there that forces your primer to only bind to its complementary sequence, but that you want lots of your primer bound. Okay, so after the annealing step comes the extension step, and that happens at about 72 degrees because that's where polymerase functions really well. So for that, right, you have your primer bound, and it can extend onwards until it falls off the end of the DNA, basically. Okay? So for this, you are actually, the DNA polymerase is actually taking DNDPs and adding them based off of this, your template sequence, so it's covalently linked to your primer, and it all becomes one sequence at the end. And then, right, chain reaction, PCR, you repeat. So frequently PCR reactions will do this 30 times or more, making many, many copies of your original DNA template. Okay, so a few things that are really important to think about when you're working through a PCR reaction. So 5' and 3' ends are really important here. So people often get confused with where the primers are going to bind and which way extension happens. So if you're working it out for yourself, it's always good to label 5' and 3' ends. Okay, and then you've got your primer, and your primer is going to have to go in the opposite direction, right? So a PCR reaction needs 2 primers kind of flanking the region that you want to amplify, and the 3' ends need to sort of point to each other because polymerase will add to the 3' end. So it will add in this direction and add in this direction. Make sense? In the next round, when these separate, these purple strands can now be a template as well. So this purple strand, right, if we imagined that our template was genome and it just continued for a long time, right, a whole chromosome. And then we take this shorter, let's just take this one, the bottom purple. So it starts here with 5', okay? So it's cut off all of that chromosomal DNA, right? And now this, and then it keeps going, right, all the way until it falls off the DNA, essentially. So our second primer base pairs with this part of its sequence. And when it extends, it'll go in that direction, remember, because this was 5'. Okay, so now we've created our final product, and all products based off of this, right, on the next round, we start with that, and now we have this primer coming in, binding right at the end, and it'll copy the whole thing. So this is what the vast majority of our sequences will look like at the end of a PCR reaction. They'll be from primer to primer, okay? And the primers are part of the product. Don't get confused about that. All right, so after our PCR, we used a DNA gel, an agarose gel, to visualize our product. So important with DNA gels are that they separate DNA based on size, and how they do this is by using the negative charge of the DNA. So if you've got a gel and you load your DNA up at the top of the wells, if you apply a positive charge to this end, the DNA will go towards the positive end. And the shorter the DNA, the faster it will go. So at the end, you have a gel where your DNA comes out in bands based on its length. Okay? Kind of like kids running through a forest. You've got a couple kids holding hands, they can move in between the trees really quickly and go really fast. If you have 20, 5-year-olds all holding hands trying to snake through the trees, they're going to get a little tangled and snagged and whatnot, so they go slower. Right? So that's why the short DNA runs faster. They all have the same charge to mass ratio, so that's not going to affect how fast they run. So the short guys go faster and will go towards the positive end.